Hello, everyone. My name is Max. I'm a final year PhD student, and I was finally able to fix it. I work under the supervision of Dr. Devika Kamath at Macquarie University, and today I will talk about how binary interaction affects the surface chemical composition of post-AGB stuff. So this is my first PhD project, and it had two main goals. First one was to understand how the binarity affects the origin of elements in the universe, from CNO up to slow neutron capture process elements. The second goal was to investigate differences between the chemical composition of post-AGB and post-RGB binary stars. For this task, I used multi-wavelength photometry from optical to near-infrared from open source catalogs, as well as high-resolution optical and near-infrared spectroscopy from ground-based facilities like Mercator, VLT, and Apogee Survey. As for the methods, the photometric data points allow us to estimate the luminosity of the star, and the spectra allow us to conduct the chemical abundance analysis. And then the integration with stellar evolutionary models lets us understand provides us with the theoretical framework. With the context set, I would like to highlight the main points. When one of the components in the binary system evolves up the giant branch, it may overfill its Roche slope, which leads to the mass ejections into the circumstellar environment, where this matter forms a stable circumbinary disk. This is confirmed by the direct and interferometric imaging observations conducted in the last decade with VLTI and ALMA facilities. Now, on the left-hand side, you can see a sketch of the post-AGB binary system. In my research, the main parts of the system are the post-AGB primary star and the circumbinary disk. Both these things we can see on the spectral energy distribution, which is shown on the right-hand side of the slide. The photometric data points are fitted with the red star model. It's the observed model atmosphere. The black star model is the de-reddened model atmosphere. I will talk about it in a while, but the main point here is that all post-AGB binaries have a common feature in their spectral energy distributions. They have a broad near-infrared excess, which points to the presence of the hot dust in the system, which is in the form of the inner part of the disk. Now, it is supposed that there is a fractionation of dust and gas happening in the inner part of the circumbinary disk, and this leads to a notable underabundance of the refractory elements, which are the first elements to condense. So the plot here shows the condensation temperature, which is a unique parameter for every element on the x-axis. On the y-axis, we have the abundance relative to the solar value. And we have two types of elements: volatile, which are harder to condense or lost to condense, and refractory elements. So the condensation as a spherical cow in a vacuum happens, as a rule of the thumb, from the right to the left. But that's, again, in theory. In reality, you can already see it on this plot, the difference between the elements which are clearly affected by depletion and those which are virtually unaffected is not at this demarcation between volatile and refractory elements, which is around 1250 kelvins. In reality, it is somewhere from 600 to 1500 kelvins within the post-AGB sample. So to track this break, there is the parameter called the turn-off temperature. And the slope of the depletion is usually tracked by sulfur over titanium or zinc over titanium abundance ratio. we cannot see zinc in this plot, but it's very close to the sulfur. And what I wanted to add here is that since these three elements share the nucleosynthetic origin, we expect the abundance ratios of sulfur over titanium and zinc over titanium to be close to zero in absentia of depletion. Overall, post-AGB sample has the zinc over titanium values going from virtually zero up to 3 DACs. Now, the preceding stage of the AGB has a lot of the stars of this stage were studied a lot for the CNO isotopes, but our stars have very piecemeal studies and only for the circumstar envelopes. And the important part here is that usually CNO elements are left out of the discussion of the depletion because they were always assumed to be heavily affected by nucleosynthesis. So there was a very big problem to disentangle which change in the element abundance is caused by the nucleosynthesis and which one is caused by the depletion. Now, post-AGB stars were known for decades, but in 2016, Kamath et al. Have discovered that binary interaction can also terminate the evolution up the RGB, leading to the creation of post-RGB stars. These dusty post-RGB stars were found to be the exact analogs of post-AGB binary stars, with the only parameters different being luminosity and the chemical composition. The luminosity was actually the demarcation parameter for post-RGB and post-AGB candidates, specifically the 2,500 L-sun, which is the rough value for the tip of the red giant branch. So all the targets below, as you can see on the evolutionary tracks on the left-hand side, all the stars below this demarcation were assumed to be post-RGB candidates. All the stars above were assumed to be post-AGB candidates. Now, the chemical composition of post-RGB stars is supposed to track the RGB nucleosynthesis, meaning the first dredge up and non-convective extra mixing happening before the binary interaction terminates the evolution up this red giant branch. Why do we care about these two things, luminosity and chemical composition? Because they provide us with the values we need to put our stars in the context of star and galactic evolutionary models: the mass, carbon of oxygen, and metallicity. So, in my first PhD project, I studied two post-RGB stars, which are type 2 Cephate pulsators. Their ACES are shown on the plot. Now, the way to calculate the luminosity from the ACES is to iteratively fit the ACES until the convergence of the main parameters. Usually, these are effective temperature, surface gravity, reddening or extinction, and the stellar angular size. However, you may remember that a few slides ago, I have mentioned that these two stars are type 2 Cephates, and it would be a shame not to use it to our advantage, because there is a period luminosity color relation for the type 2 Cephates. We use the calibrated equation based on the OGLE4 data for type 2 Cephates in LMC. And you can see the equation at the bottom of this slide. The resulting values are way below the RGB tip of the RGB. So we confirmed the post-RGB nature of these two stars. Now, with the luminosity set, we can study the chemical composition. And the way to do it is to use a chemical abundance analysis code. The problem here is different research groups use different spectral analysis tools. And most of the present spectral analysis tools are performing poorly for the evolved stars. So major part of my PhD was to develop a tool to use it with our peculiar targets. And that's what I did. There is a very well-known code called iSpec. I created a modified version of this code, which is streamlined for the evolved stars. So the major advantage of vanilla iSpec is that it allows you to seamlessly switch between different radiative transfer codes, which are usually used by different research groups, so that you can more easily compare the bulk results for our population of targets. And also, vanilla iSpec has a large selection of model atmospheres, solar abundances, and line lists. Now, I kept the advantages of iSpec and streamlined it for our evolved stars, and our main additions were the addition of manual normalization routine, the update of the near-infrared line list, the calculation of total abundance uncertainties, the treatment of isotopic ratios, and in collaboration with Dr. Anish Amarsi, we used the Balder code for non-LT corrections heavily. So I modified the iSpec so that it can take the output of the Balder and plug it in as the input for the calculations of updated abundances, atmospheric parameters, and the uncertainties of these values. So, going to the results, I will quickly refresh what we have in this plot. We have the condensation temperature, which is unique for each chemical element on the x-axis, the abundance of an chemical abundance relative to solar value on the y-axis, and the studied ionizations of each element are shown in the top part of the plot. The optical and near-infrared abundances are shown with black and red dots respectively. To have some quantitative turn of temperature, I have fitted all abundances except CNO with a two-piece linear fit. And you can see the rough numbers for these turn of temperatures in the legend. Now, overall, we can see that we have found that the depletion is milder for post-RGB stars than the average depletion in post-AGB sample. And the turn of temperature, which is, again, around 1300 kelvins, is way higher than the average turn of temperature within the post-AGB sample, which is around 1100 kelvins. Also, the surface carbon isotopic ratios in our post-RGB stars are mostly in line with the circumstellar values from the literature for post-AGB stars. Now, when we have luminosities and chemical composition, we can compare it with the models of single-star RGB evolution. We assume that our post-RGB stars, again, are showing us the composition and the luminosity, which was before the evolution up the giant branch was terminated by the binary interaction. So we have Asimov plots on the left-hand side, DF-SIG plots on the right-hand side. For all panels, the x-axis is the luminosity, which tracks the evolution of the star. And the top, all the panels have the abundance measure. The top panels show the evolutionary run of the carbon isotopic ratio. The bottom left panels show the nitrogen abundance, and the bottom right panel show the evolutionary run of carbon over oxygen ratio. The three models that were tested were the first dredge up without extra mixing in black, first dredge up with extra mixing in red, and first dredge up with very deep extra mixing in blue. The observed values within the error bars are shown with the gray boxes. And as you can see, first of all, the preferred model for both stars is first dredge up with usual standard extra mixing. And you can also see the potency of using carbon isotopic ratios over the less precise total abundances of the main element. Now, the main takeaway here is the abundances of CNO isotopes, in post-RGB binaries reflect the RGB single star predictions from first dredge up and deep mixing. So I will stop here. I'll just mention that EISPEC is a very fast and potent tool for analysis and derivation of atmospheric parameters, elemental abundances, and isotopic ratios of evolved stars. Using EISPEC, I have derived the first photospheric carbon isotopic ratios in post-RGB stars. We have found that the binary interaction in post-RGB stars does not seem to affect the CNO nucleosynthesis, and that post-RGB depletion profiles have a lower zinc over titanium ratio and higher turn-off temperature than post-AGB average sample depletion profiles. This last point was also confirmed in the current project I'm working with, which has a sample of potentially planet hosting post-AGB and post-RGB binary stars. And the open questions which our research group is working on right now are how the binary evolution affects the CNO elements, what causes the chemical depletion to be different within post-AGB and post-RGB sample, and how the equilibrium conditions of gas phase change within our sample. With that said, I thank you very much for your attention, and I'm open to your questions.
Hi, Max. Thank you for a great talk. So my question is related to your comparison between the models and the observations. So the post-RGB progenitors are under no obligation to actually complete the first dredge up. So you might only have like partial enhancements of first dredge up elements. Is that something you take into consideration when you make your comparisons?
Thank you very much for your question. Yes, of course. We take into account that the model run, the stellar evolutionary models that we use are actually include when the dredge up episodes happen within the evolution up the giant branch.